Now, when you solve for x, it was pretty simple. That 0.2 just moves right over there. And take the cube root. And I don't know if I can remember this from memory. The last 2 hours. The x gives us the hydroxide concentration, which is what the question is asking for. No, I guess it's not quite, because the question is what is the pH? So we're going to have to change the hydroxide concentration to a pH value. 4 point something times 10 to the negative 11th. Anybody have it? 4.6? Okay. 4.6 times 10 to the negative 11th molarity. Now notice, and you may have kind of caught this, I just changed my greater than inequality sign to an equal sign. Is that okay for me to do? When you get into taking logs of number, from an inequality, taking logs and finding a pH, it is a little bit weird to use an inequality sign. So I just went with the equal sign to say this, that at that hydroxide concentration, we're right on the edge of making a precipitate. Okay, it's right there on the brink of it. So I'm fine with just changing the greater than sign to an equal sign. The pH, you'd find the pOH from this, take negative log of this, subtract 14. You get a pH like 3 point something. This pOH is 10 point whatever, and then subtract 14 is going to be 3 point whatever. Yeah? Okay, so you'll have to do problems like this that ask you, will a precipitate form or won't it? Like what does the concentration of something have to be to just start making precipitate, that kind of thing. So these problems aren't terrible. You just use the Q value as a greater than or less than K. Now the next type of problem that we're going to be contending with, I'm going to cover part of this up because it's a little scary looking. I'm going to do the same technique. Now, I don't know that you have to write the entire problem out. There's a lot of words on this slide. You can just write down number 55 for yourself. It's right in the book. The title of the slide now is Concentration After Precipitation. So the problem is going to start the same way. You're going to take two solutions and combine them together. It's probably going to make a precipitate in this case. And the question is, what are the concentrations of the ions after a precipitate is made? So it's going to shift this way. It's going to make, I don't have the chemical equation, but it's going to shift from ions to make some solid. But then what are the concentrations at the end? That's what we're going to have to do with the problems like this. This is going to take a little bit more work. All those zeros are kind of obnoxious. I'm sorry about that. In the first problem today, you had to figure out what combination of ions would make a precipitate. Sometimes the problem just makes it easy for you. Can you tell what combination of ions are going to make the precipitate? How does the problem make it easy for us? It gives us the KSP for something. That's going to be the one that is the precipitate. So that's very handy. So the silver ion is going to leave the nitrate. The iodate, IO3 is iodate, just like ClO3 is chlorate. So silver, iodate, they're going to find one another and make a precipitate. They're not very soluble, so that's not likely to precipitate in this case. Now here's what we're going to have to do. The technique for finding what the concentration after precipitation happens is going to go like this. It's probably not going to make a lot of sense until I show you how to do it. But the first thing is, when you need a concentration at the end, I want you to assume that the reaction will precipitate to completion, which means that something one of the ions has to run out. So have it go to completion to make the precipitate is the first step. Now the second step, I'm sorry, it's very wordy. I don't know how to cut the number of words down. Once you have brought it all the way to the left as far as it will go, the reaction that is, then it needs to drift back to equilibrium. And that's when you're actually going to find the concentrations. So we'll go through this problem together. I'll show you what I mean. So at the end it says modified ice table. What do you mean by modified ice table? You've never done that. Yeah, then there's something new. All right, can we try this? I'll try to get the problem at the top of the screen. All right. Sorry about all these words. Let's see if we can do this thing. So this is going to be our precipitate, the AgIO3. Let's go ahead and write the chemical equation. AgIO3 solid is going to break up into silver ions plus iodate ions. And we know its K value is given to us, 3 times 10 to the negative 8. What are the initial concentrations of the ion? Okay, well, let's see. 50 milliliters of each solution. Again, that's very nice when they do that because that allows us to just take the concentrations that originally were there and cut them in half. The volume's doubled, concentration gets cut in half. So the silver ion concentration was 0.002, but when it got diluted by a factor of 2, initially its concentration is 0.001. Same thing with the iodate ion. It started as 0.01 and it got cut in half to 0.005. So those are the initial concentrations. Now, I guess the next thing that we have to do, and it's probably not appropriate to assume this, we can't just assume that the reaction is going to shift left and make precipitate. We need to check the Q value on these concentrations. So the Q value would be silver ion concentration times iodate, which would be 0.001 times 0.005. And that would give us a Q value of, let's see, this is 1 times 10 to the negative third times 5 times 10 to the negative third. That'll give us 5 times 10 to the negative sixth. Yes? Is Q bigger than K? Yes. It's a lot bigger than K. It's a couple hundred times bigger than K, at least 100 times. So, yeah, this thing is going to shift to the left. And this is what I'm talking about here in number 1. Assume the precipitation goes to completion. So that means we have to look at both ion concentrations. Which one is smaller? That's going to be the limiting reactant. The silver ion concentration is small. So the reaction is going to, I'm going to make a C here for change. The reaction is going to change by shifting left, because Q is bigger than K. And it's going to cause the silver ion concentration to go down to 0 as the precipitation happens to completion. The IO3 then goes down by the amount that silver went down to 0.004. Now again, this on the left side is a solid. So I don't really have a concentration to say that we made. However, we just know that, and I'm going to put this kind of weird, but I'll just put some solid was made. So the solution is going to get cloudy, or there's going to be precipitate at the bottom, or some sign of a precipitate is going to be there. We've learned in the course of doing all these equilibrium chapters that you can't stop here. We can't be done here. Can silver be 0 at equilibrium? No, you can't have anything with a concentration of 0 at equilibrium. Equilibrium means that the reaction is going to proceed and we'll have some products and some reactions. You can't, reactants, you can't have 0 of anything. That's one thing you need to know. If you have 0 of something in an equilibrium reaction, it cannot happen. You're going to have to make some of it, so the reaction is going to shift to make some. So that means this, and this is where I'm going to make this modified ice table. The reaction changed when it came back this way, but it came back all the way. Now, it's got to drift back to the right. A little bit, not much. And that means that we're going to need another change line. So it changed coming left, now it's going to have to change going back to the right side until we can finally arrive at equilibrium concentration. So this we would not call an ice table. We'll now call this modified ice table an ice table. Like we're from the South. You can practice saying that at home, and we'll try it tomorrow together. Okay? All right, so some of that solid now then has to again dissolve and shift to the right, which means this is going to go up by x, and the IO3, even though we already had some, is going to go up by x as well. All right, so at equilibrium, again, this is a solid, so we really don't have a concentration of it. That silver started at 0 and went up by x. The iodate started at 0.004 and went up by x, so it's 0.004 plus x. Okay, and now, finally, we can do the calculation. The KSP is 3 times 10 to the negative 8. So we need that now. KSP equals 3 times 10 to the negative 8, and that's equal to the silver concentration, x, times the iodate concentration, which is 0.004 plus x. Is that x small enough that we can neglect it? 0.004 is pretty small already, but is x small enough that we can neglect it? I hope so. But let's try the 5% rule. Let's go ahead and neglect it. We'll check it later. So finding x now with that correction, or that approximation, is really easy. You just take the k value and divide by 0.004. And let's see. The k value is going, not the k value, sorry. The x value, which is the silver concentration, if we can be reminded, that's what the question was asking for. What is going to be the silver concentration at equilibrium? So when we solve for x, that's our answer. And that's equal to that divided by 0.004, which is 7.5 times 10 to the negative 6. Is that